Okay, that's lecture 16, cap 2. Again, further applications of integration, and this is section 2, applications to physics and engineering, hydrostatic pressure and force. Okay, now what is pressure first? Pressure is force over area. You might have seen this on your car tires. It says PSI. PSI is pounds per square inches. So this is force over area. Okay, so now our problem is suppose we have some object which is submerged in water or some liquid. So some object which is submerged somehow, let's assume that it is submerged vertically, so it's like this, not like this. Then we want to find force applied by that liquid to this object. Okay, so we have to, this object has some area, we would say, and we know that the pressure is force divided by area. So to find force, we should somehow multiply pressure by area. So force will be pressure times area. So we want to find force on this thing. So we find dF. So we find dF. And what we do here, we put that differential on A. So we multiply P by dA, and that is our differential of force. Now, it's not always like this, it depends on the situation, but for us and for hydrostatic pressure, this is the case. Now, so we need that pressure and some formula for pressure when something is submerged in water or maybe some liquid. Now, it can be shown in fact, we can prove this thing in fluid mechanics that pressure when something is submerged at certain, say, distance from the surface, so this is the surface, and you have like a point here at distance h, depth h, and the liquid has gamma as weight density. Weight density of the liquid, then pressure at this depth is simply gamma h. So it's gamma times depth. It doesn't matter how much water is above this thing, it's not how much. It is where it is. It is where it is. So if you ever take a fluid mechanics course, they might prove this to you that pressure at this depth is in fact the weight density times height. I don't know, I mean depth. So this also means that this pressure is a function of this h. So it makes pressure as a function of depth. You see? But it's a very simple function, it's linear, right? It's the linear function. But it is a function of h. So it's like a line. So if I look at this object here in this, so if well, let me erase all these things and so this, say this is like something which doesn't have, it's something like this, okay? So something like this, submerged like this, And here I'm looking this way. Now let's look at it this way, from this side. So if I look at it from this side, or this side, then I see something like this, just an object like this. Something like this. So let's assume that the thickness is fixed. Okay. Now, what happens is this. This formula gives me a pressure. So pressure at this point is 0. And then it linearly increases. The pressure linearly increases. So it goes like this. It's 0 here, it linearly increases up, goes to this point. Okay? And I can draw some like a vector for that. So pressure would be something like this applied to this object. Okay, so at level H, at depth H, this guy here is gamma H. This vector is gamma H. Magnitude of the vector is gamma H. So, how can we find force? I cannot multiply any one of them by the area, right? Because it's changing. This force is changing on this guy. So the force, if I had a force which was always like, pressure which was always like this, pressure everywhere the same. So I will multiply the pressure by area and get force. But this pressure is changing. It gets larger and larger. And if this object has some, say, width or length or whatever you call it, if this is large enough, then it changes a lot from here to here. So it's like this here and right here like this. So as you go deeper and deeper, the pressure is higher and higher. And that's why if you have a submarine and is something that has to go deep into the ocean, it has to be very strong to take that force which is applied, which is produced by pressure at deeper, when we go deeper, say. So how can we do that? Well, it's very easy. We simply, as I wrote down for you, the d of force, I wrote it as P as a function of H times dA. And this dA should be a function of H, right? So if I am at level H here, then I can draw this line. Then I can go further down by dH. Okay? And this is my area, dA. So this is the dA. So my job is simply finding dA. But what is dA? dA is this length, which is L as a function of H times dH. So my dA is simply that L dH, and L itself depends on H. So if I can find this L as a function of H, then I have this thing. So this will be P as a function of H, L again as a function of H, and dH. So the force will be integral from, say, I don't know, maybe A to B. So this starts here at A and goes to B. This is H here and H here of this dF, which is A to B, P as a function of H, L as a function of H times dH. Okay, so we go back to those basics. What is this L? L is like a cross-section, right? L is like a cross-section, and that's all you have to do. When given some shape or something, you have to find the cross section as a function of depth, and that's it. That's all you have to do. And also pressure. Pressure is this gamma h. So let me write it here. So we have integral AB gamma h, LH, and DH. So in the end, again you see it is simply finding this cross section. Okay, so let me give you an example, which is usually examples are like this. I mean, problems are like this. So if I have a, say, something submerged, one of the things that is submerged in water is a dam. So, one dam. So dams are submerged. Dams look like this, something like a trapezoid, for example, and then water is up to some point here. So this is surface, and then dam goes down. So it's important for civil engineers, those who design dams, to know the total force applied to this, and also they also work with pressure to find stress and strain in this dam, and then design it accordingly. Okay, so let's say gamma is just gamma of water, and well, we can just take this dam hull. Let's just make a nice example in the book, and it says a dam which height is 20, so it says the height is 20 meters. So it says in the book that example that is 20 meters SI units, and then it is 50 on top and 30 here. And what else does it give me? And then we will find the force on the level is 4 meters from the top. So it is, the level is 4 meters from the top, so it is here, 4. Okay, so let's find force applied to this. So if I look at it from this side, I see something like this, right? And this is 1, 2, 3, 4. So it starts here, say, and the pressure profile is like this. So this is the pressure profile, linear. Okay, so this is the pressure profile, and okay, what do I need? I need this. If I set, I can set so this is like the origin, say O or whatever you call it, then at a certain level H, say, I should find LH. This is L as a function of H. Okay. So that's all I should do. So that's a simple high school geometry, right? So, well, let's see. Let me erase this profile and see if I can find this thing. So, I have this situation, a trapezoid, and this side is 20, say, and this is 50, and this is 30, and this is 4, and then down here is H. So, and I need this thing. One way I can do this is draw and this is an equilateral trapezoid, which means these two sides have the same size. So if I draw a line parallel to this, so I draw a line parallel to this, so this is 30, this is 30, so this part is 20. And so this is also 30, so I need this small portion. Well, let's call it something like x. And how much is this? This is 20 minus 4 plus 8. So this is 20 minus 4 plus 8. And the whole thing is also 20. Yeah. The whole thing is 20. So I have x, this x over 20 is this height, which is 20 minus 4, which is 16, minus h. Is 16 minus h over the whole thing is 20 again. So this is 20. This is just coincidence because the 20 and the 20 they cancel out. It doesn't happen all the time, but anyway, so this gives me that this x is 16 minus h. So L, which is 30 plus x, will be 30 plus 16 minus h. So it will be 46 minus h. Okay. So I have L. And gamma of water is, I think that's 9800, right? Yeah. So gamma is rho g, which is 9800. So that's gamma, and what else do I need? Nothing really. So I just need this L as a function of h, and then the force will be integral. If I start here, because h goes from 0 to 20 minus 4, that is 16. So h goes from 0 to 16, and gamma h times LH times DH, right? So that was PLDH, that is from 0 to 16. Gamma is 9800. LH was 46 minus H, and DH. Okay, that gives me, the book has 4.43 10 to the power 7. Newtons. And look at this is a huge number. So, that is a huge number, in fact, it should be. Anyway, so that is how you do it, and this is a simple problem, except it needs some geometry. Well, I'm not saying it's always geometry like this. This is similarities, which I use similarities in triangles. It might be that you might even use, say, I don't know, like if something like a circle or an ellipse is given to you, you have to use equations of the circle or the ellipse. So that is how they find the total force on a dam, which is like this, of this shape. Okay, so that was hydrostatic, pressure and force. Now, before I stop, if you have something which is not vertical, I leave that to courses that you might take if you ever take any course like in statics, for example. We might discuss this in statics. So it might, this object was like this, but it might be like this, then what happens? Well, I'm not going to discuss this one, but I did discuss this one, which is the simplest case. So if the object is like this, well, it's very simple. If the object is, if this is, say, the surface and the object is right here, down here, then it has an area, and if the height is h, so the force on this one is simply gamma H, which is the pressure times A, PA. It's that simple. So if it is like lying like this at the bottom of, say, a swimming pool, for example, like this, then simply multiply the gamma H by surface area. So this, what I discuss here is when it is submerged like this, not like this. Okay? Vertical, not horizontal. So if you have horizontal, then it's simply gamma H times A. Okay, so that was hydrostatic